In this video, I will explain how electronic circuits count. In order for my video to be interactive, I will include a decoder and a 7-segment LED display. The decoder used here accepts a sequence of voltage on its input, called the BCD code or binary coded decimal, and translate that into another sequence of voltage that will lit up specific LED segments to form digits. The LED used here is called a common cathode because the negative side of all segments are tied together internally. The LED and the decoder must be of the same type, meaning if the output of the decoder is common anode, the LED must also be common anode. You can mix them, but the output of the decoder would have to be knotted. The decoder also have other features, but I will explain those later. In order to understand counters, you must learn about digital electronics and binary number system. There are two discrete voltage levels used in digital electronics. One is called high and the other is called low. Voltage levels of 2.0 and above is considered high, and voltage levels of 0.8 and lower is considered low. 5 volts has become the standard for high in TTL circuits, so we will use that to represent high. We will use ground for low since it's normally 0 or close to 0. The digit 0 and 1 is also used to represent these voltage levels. 0 represents low and 1 represents high. So if you take a look over here in this counting in binary chart, this means 5 volts, 5 volts, 5 volts, 0 volts. Likewise, this means 5 volts, 5 volts, 0 volts, 0 volts. In order for the decoder to count, we must place these voltage levels on the input pin over here. So, for example, if we want the digit 5, we have high, low, or 5 volts, 0 volts, 5 volts, 0 volts. So we would place this code on the input of the decoder. So that would be high, low, high, low. So that's high, low, and the decoder would display 5 on the LED. So any digit that you want to be displayed here, you would have to get the code from here, whatever code it is, to make that digit appear there, with the exception of 10, of course, because it's only one digit and you can't, obviously display 10 with one digit. So just ignore this code for now. It's used later on in this illustration. As an example, if we want 4, we need to have low, low, high, low, right? And that's it right there. Okay. Now I don't know if you're taking notice to what's going on here, but you have to know the specific sequence to put these codes and these pins. What I mean is, for example, the code for 4 is low, low, high, low. And pay attention to the fact that I'm starting from my right and moving to my left. Now, we need to put that code as input to the decoder. Now, where do I start to put this code? Because, for example, if I say low, low, high, low, that is low, low, high, low. See what happened? I get 2 on the display because I start from the wrong direction, putting the sequence on. The proper sequence is low, low, high, low, and we have 4 and not the other way around. To place these codes in the proper order, you must understand the binary number system. The binary number system has place values similar to decimal. For example, in the decimal system, this is the ones place, tens place, 100 place, 1000 place, 10,000 place, etc., going towards the left. In the binary system, the first place is called the ones place, then second place, fourth place, eighth place, 16th place, 32nd place, 64th place, going towards the left in a similar fashion as we have decimal. Now if you look at the input to the decoder over here, you will see the place value listed also. So this is 1st place, 2nd place, 4th place, 8th place. So we're only using from 1st place to 8th place. If you look at the binary digits over here, this would be the 1st place, this would be the 2nd place, this would be the 4th place, and this would be the 8th place. So if we want 8 to be on the display, we would put low, 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 high. And of course, we only need a high in the 8th place, so that means this pin is the pin that we send high and not this pin. Likewise, if we need a 1, we would place a high in the 1's place, and that would be this pin. In decimal, each place value is called a digit. The leftmost one is called the most significant digit, and the rightmost one is called the least significant digit. In binary, each place value is called a bit. The leftmost one is called the most significant bit, and the rightmost one is called the least significant bit. In any number system, the least significant will be the one that changes most often. So this will be 5 digits, and this will be 8 bits. This would be 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 6 bit, 7 bit, 8 bit, 9 bit, 10 bit. This pin is called ripple blanking, this pin is called lamp test, and this pin is called latch. Both the ripple blanking and lamp test pins are active low, meaning that they need to see low before the extra features will kick in. The latch pin, on the other hand, is active high. So whenever this pin goes high, it will activate extra features. Now the ripple blanking pin, there is nothing for me to actually experiment with it right now other than to just use it to blank out the display, but basically it is used to blank out the display whenever you don't want the display to show anything. For example, if you say you're designing a calculator and you're going to zero the calculator, you don't want the whole screen full with zeros, you just want 1 0. So you would use this feature to block out the LEDs that you don't want to show a 0. In our case, when I bring the pin low, it simply blank the display. The lamp test pin will light up all segments in the LED. So you could use it as a test. If you want to test, make sure all the segments are working or connected properly, you would push this button and all segments will lit up. The latch pin, whenever this pin goes high, it will freeze whatever number is on the display. Basically, it would just make the decoder inactive. So for example, if I have, say, a 6 on display, let's make a 6. I put in these 2 pins high, and I turn the latch on. Now, if I zero back the decoder, come on, it's still saying 6. Now, if I try to put another number on the decoder, say for example 2, low, high, low, low, that would be this one, still nothing happened because the display is latch. If I release the latch, now I would see my 2 because now the decoder is no longer latch. So that's the purpose of the latch. So now the decoder could operate as usual and, display any number that I put on it. So that's it for this section. Let's move on to the other section. Here is the complete counter circuit. This is the counter section and this is the decoder section. Now before I explain how the circuit works, I will test the circuit so you could see that the circuit actually generates this sequence of number here. in ascending order. Pay attention to these logic indicator here. They will lit up in the same sequence as the codes appear. For example, if I have the code low, 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 high, you will see this one off, this one off, this one off, and this one on. Okay, so here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and back to 0.